Okay. Well, you guys saw me talk for a while, but now it's working. So welcome again to Beyond Scope. Today we have Matt Cabral give a talk. He did his graduate work at North Carolina State University. Did a lot of electron microscopy work there, aberration corrected TM STEM work. He did postdocs at Australia, American University, but then also at Carnegie Mellon before coming here and working with the STEM team. So he'll be giving a talk on inorganic sample preparation. And for upcoming talks, we'll have one with the Student Microscopy Organization next month. And then Hank will be giving a talk about vacuum systems. So all the guts of the microscope, the behind the scenes things you don't think about too much that are very important for electron microscopy. And then we'll go to a science talk with postdoc Shriram giving it on some of his work with multi-scale, multi-correlative microscopy work across basically all the instruments here at CMAS. So excited for that one as well.
Yeah, Matt. Sorry, thanks, Dan. Thanks for the introduction. Thank you for those here, and thank you for those that are watching remotely. So, today's talk, I'll be discussing a couple of the techniques for preparation of inorganic samples for electron microscopy in the SEM and the TEM. The two different instruments, for the most part, have fairly similar sample preparation methods. You're just looking for different things. But please feel free to ask questions, and we can go over them throughout the presentation and at the end. So just a little bit about me. So me and Dan are on the scanning electron microscopes here. So if anybody's interested in getting trained or looking at any interesting materials, just feel free to contact us. So an overview of the equipment we have here at CMAS. We have a large suite of electron microscopes. We have the high-end TEM instruments, including the aberration corrected instruments. We have a couple of cryo electron microscopes, focused ion beam for sample preparation, and finally, what tools that myself and Dan work on are the scanning electron microscopes, notably the Abrios and the Quattro. So just a brief introduction about myself that Dan went over briefly. So I did my graduate work at North Carolina State University. I originally was working in nuclear engineering, where I studied radiation effects in materials, and that's where I got my first introduction to electron microscopy to try to see if we could observe anything. But then I switched over to material science and engineering, where I did my PhD, where I did aberration corrected STEM on ferroelectric materials. I did postdoctoral position at the University of Sydney back from 2019 to 2021. And then I worked in the characterization facilities at various universities, NC State, Carnegie Mellon, and then here at Ohio State. So just a brief overview. So we'll break this down into sample preparation techniques for the SEM and for the TEM. We'll talk about some of the common techniques. This is by no means all-inclusive, just because there are dozens of ways you can prepare your samples. But hopefully this gives you an idea of what we need to do to get the sample ready for imaging. So when you're imaging your sample in SEM, there are numerous things you have to consider on not just for the sample preparation of these materials, but for your imaging conditions and the techniques that you use. So for things like PDS and EPSD, feature size is very important. Then there are things like sample size and weight, geometry, and if your features in your image will produce contrast, and sometimes sample preparation is important for that. It's vacuum compatibility and how it behaves under the electron beam. So to get your sample ready, there is actually no real set path, but this is kind of a general overview of the steps that you typically need to take to prepare your inorganic samples for electron microscopy. So just remember, there's no set recipe, and certain steps could be entirely skipped or done multiple times. So usually if you start with a larger bulk material, you want to cut that into a section that is representative for scanning electron microscopy. You want to mount the sample for rough polishing and then move on to fine polishing, cleaning. For certain samples, you might need to do etching to gain contrast from certain features. If your sample is non-conductive, you will need to coat it or use other techniques. But I'll go a little bit more into that. And then once you get your samples ready, you can finally do your analysis. So I'll actually go through all these steps throughout the next few slides. So cutting and sectioning. So this depends a lot on your material. So there are many ways of sectioning your sample down to to a size that is usable for what you're trying to do. But it depends on the type of sample. So if you have a piece, if you have something on silicon, you can just easily cleave that. If you have a large chunk of metal, you need to use a high-speed saw. If you have something a little bit more delicate, you would need to use a low-speed saw, such as this one here, or a wire saw. But there are actually a lot of considerations too when using these, when just even sectioning your sample. As you can see here, there are various fixtures for the saws that you can put in odd-shaped samples and get ready to cut. So when cutting a particular sample, you want to keep in mind the saw revolutions per minute, how much load you're applying to your sample, the type of blade you use. There's dozens of different kinds of blades that are more optimal for something hard like perhaps a diamond substrate, or if you're cutting something ductile, they make these waveframe blades that are optimized for that. Likewise with load, if your sample is brittle, you don't want to actually have a high load on that because it could crack under the applied weight and under the sawing. And for cooling, so usually you can use water for a lot of samples. If your sample is water sensitive, you can use something like various oils that are made specifically for cutting. So mounting is what you would do to get your sample in a secure position so that you can polish it. So here at Ohio State, a lot of people do metallography, and they typically use these epoxy mounts that they embed their sample in with their region of interest exposed. So you can use that to embed your sample if you need to have, which is useful for exposing different parts of your sample that you might want to polish. For polishing, there are various fixtures that you can use to secure your sample. You can see a couple of examples here. In many cases, some people could use super glue, or they could use crystal bond to just attach their material, or you could physically clamp it into a fixture that will allow you to polish a region of interest. So in some cases, if you did something like you did a tension test, you want to look at that sheared area, your sample could be already ready for the electron microscope because you don't want to necessarily polish away any of that deformation. But if your sample is ready, in many instances, if your sample is, say, large and flat, you can just simply lay it on the stage here in the STM. Other things you can use are these aluminum stubs where you can secure your sample down with various kinds of tape or with conductive paint such as graphene paint or silver paint. So the first step is when you get your sample mounted properly, is to do rough polishing. So this typically involves removing coarse layers of materials to make your sample flat and to start to achieve smoothness. And historically, this is done by hand. Some people still use that technique by physically polishing it by hand on various polishing media, but there are tripod systems now, various that are configured for various size samples. and you can polish down your samples with that. So there are these polishing films that have different materials that can remove that are used to remove material. So you can use something like diamond, silicon carbide, or alumina. The choice of these just depends on your sample itself. If you have a very hard material, you definitely want to use diamond, but those are more expensive than they would be the alumina lapping films. So with this, you want to do a forced polish and at a higher grit film, and then work your way down to a finer grit film to progressively remove the damage from the previous grit. So a general rule that we typically use for polishing samples is, so as you polish, you increasing grit size. So you want to remove at least 3 times the grit size of a previous film on your current film. So if you polish with a 30 micron grit film, when you move to the 15 grit film, you want to remove at least 90 microns of material with that 15. So when you move to something like the 9, you want to remove 45 microns. And that's just a general rule of thumb, just to make sure that you're removing those damage layers, which could be, if you don't remove them, they could hinder some of the analysis that I'll talk about a little bit later. So for fine polishing, there's various techniques, but you can use these liquid abrasives. So there are diamond based, and then there's one of the commonly used ones is colloidal silica, which is a suspension that has small silica particles that are various diameters. So in my experience, I typically polish down to about 0.02 micron of particle size to remove the damage from the previous layers to achieve a mirror-like finish. So these are great for removing very fine layers. So it's important to note that if you go right to this step and don't do the rough polishing with progressively moving down, you might achieve a nice mirror-like surface, but you still have several microns of damaged material that will then hinder your electron microscopy. So this is an important aspect of it, but it's typically what is useful for getting that very fine mirror polish before you go into the microscope. So another commonly used technique is ion milling. So there are various systems available that use broad beam argon ion milling to remove damaged layers. So in some instances, I've talked to people who've done their sample prep completely with ion milling. It's just a matter of how much time you want to actually spend doing it. But you can typically configure an argon ion mill to mill between energies of 100 electron volts and 10 keV. And you can modify your beam diameter to be microns to millimeters in diameter. In addition, you can use liquid nitrogen cooling to mitigate damage as you remove those layers. So with these, with higher energies, what you typically want to do, just like you would in polishing, is you want to do a rougher ion milling with a higher energy, and then progressively work your way down. One thing that I didn't put here that you can also do is change the angle of your guns to be at a steeper angle or a shallower angle, which as you get the shallower angle, that helps get the top layers polished. And you can see one example here of before and after ion milling makes a significant difference in your sample quality, and with the added advantage of you don't have to necessarily worry about things like the polishing, such as maybe you would introduce deformation into your materials. So this is definitely an option for some sample preparation. So after you're done with doing your rough polish, your fine polish, and any other additional polish, you want to make sure your sample is clean. So typically, after you finish polishing the material, you want to sonicate it in acetone to remove any oil and grease from your sample if that's present. After you do the acetone, acetone leaves a lot of residue on your sample. So you want to use something like isopropanol or ethanol to use to remove that, to remove the contamination from the acetone. And once you do that, you can you can air dry your samples to have a pretty clean surface, at least by eye. So one thing that you could still have on your sample is a thin layer of hydrocarbons. So if you have this thin layer of hydrocarbons, you won't see anything by eye, but once you put the electron beam on this area, you'll start to see this contamination build up on your surface, which can hinder your analysis and make your images not look very nice. So a couple of options for that: you can bake your sample in an oven such as this one that we have here at CMAS, but you just heat up your sample to, depending on the position, 120 or 160 degrees C, I think, and that helps to get rid of those organics. The other option is plasma cleaning, which is very effective for removing these contaminations. So similar to how the ion milling system works, is you generate a plasma with you can use various gases. So typically you can use argon, oxygen, nitrogen, in some cases hydrogen, and you can remove those from your sample. So there are external plasma cleaners like this, but there are also ones that are actually built into the STM that are also available to use if you need to clean your sample. I mentioned earlier that some additional steps might be needed for sample preparation. So for a lot of the metallographic work, sample etching is needed to gain contrast. So if you have your sample mirror polished, you might have very few features in your sample that might generate contrast in the STM. So in this case, you can use etching that will remove material at various rates. So etching, depending on how you do it or the chemical you use, it varies significantly from one sample to the next. So this can vary based on if you have different various compositions in your material, you have different phases, you have different orientations. That all affects the etching rate. So there's a whole there's a ton of literature out on etching processes for different materials. So there's no way of just highlighting one light bulb. For carbon steels, typically the first step in trying to do this etching process is with nitric acid. Again, this isn't necessary for all materials, but it might be necessary for certain metallographic samples. So sample coating. So typically for metals, you really don't have an issue with having your samples be conducted in the electron microscope. But as you move into some materials like ceramics, or in some cases when you mount your samples in the epoxy, that might be non-conductive. So that could cause some issues in the electron microscope, especially if you're using high voltages and beam currents. It could have a difficult time dissipating that charge. So typically we can use evaporation or sputtering to deposit various materials on your sample. So there are various examples. The most commonly used one is gold, but there's other options too, such as platinum, chromium, tungsten, or carbon. So there are different advantages for what you coat with. So gold is very easy and quick to deposit. It's stable in the electron beam, but there are large grain sizes. So if you're trying to look for a feature that's on the nanometer scale, that if the grains on that gold could interfere with what you're actually trying to observe. So as you look at the different options, so for gold palladium, it's similar to gold, smaller grains. Platinum is inert conductive, but it has a large grain size. Chromium has the smallest grain size, but it oxidizes rapidly. So if you deposit chromium, you probably have to image your sample very quickly. So carbon is also very common. And this is actually very useful for TEM as well in a lot of cases. I'll discuss a little bit more later, but if you're trying to do electron backscatter diffraction, you can't put something like gold on your sample because that'll interfere with your diffraction backscatter signal. So you would use carbon. I mentioned earlier, sometimes you would have your sample might be a non-conductive epoxy. In that case, you can use something like copper tape to form a conductive pathway that helps dissipate that charge. In some cases, your material will just charge a little bit, where using the tape to form that pathway will deal with the charging. And we have other talks that were given previously that talk about low vacuum SEM, which is also a viable option for materials more commonly used in biological samples, but definitely still an option for inorganic samples. So these I started with sort of like the conventional ways by polishing by hand. So the in certain instances, sample preparation can also be done in the FIB. So this is the focused ion beam, which is usually used for preparing TEM samples. But in this case, you'd use a focused ion beam, historically of gallium ions, but in current systems, there's also the option of using plasma, such as xenon, argon, oxygen, nitrogen. And I'll talk about a little bit more about the differences in those. But the advantage here is that you can target a specific area of preparation. You can cut samples in cross sections in various orientations. And you can mill weight materials with different phases and compositions, typically uniformly, but there could be some considerations in that as well. But and you can also use cryo-FIB as well if you need to do this process at low temperatures. So in terms of disadvantages, the larger area you get, and especially in the case of the gallium FIB, it takes progressively longer. If you were trying to mill an area 50 by 50 microns, that would take a very long time to FIB. And this can still introduce some damage into the process that you must progressively remove with smaller ion beam emissions. In addition, in the gallium FIB, you have gallium implantation that could interfere with some of your EDS analysis. So this is just an example that I found of sample preparation for a planar view sample in the FIB. So you can utilize different tilting geometries and mounting geometries to thin your area of interest. So there's actually a lot of options for this, which is what makes it very attractive for TEM as well. But you can use it you can manipulate your sample to get the area and orientation that you want. So, so plasma FIBs are becoming increasingly more common. So the difference between these systems is that they use a plasma, usually xenon plasma, instead of gallium. So the biggest difference between a gallium FIB and a plasma FIB is the plasma FIB can run at much higher beam currents, typically on the order of microamps compared to gallium FIBs, which are on tens of nanoamps. So you can do a much larger area. So the trade-off is you have a smaller current density. So it makes it more difficult to do precision milling and thinning, which is very important for TEM preparation, which I'll talk more about later. But in some systems, there are specialized holders that such as in thermofisher instruments, they have something called a spin mill holder, which actually lets you tilt your sample in the negative direction. So I believe without this holder, you can typically tilt minus 10, minus 15 degrees, but this lets you go to minus 38. So you can orient your sample so that you can clean the surface off with your plasma FIB instead of having to do unique mounting or tilting. And you can see that this has been used to get some pretty nice contrast in polycrystalline materials. So I didn't start with this, but in many cases, the easiest way of preparing any type of sample is to just, if you have particles, just disperse it on substrate, or you can disperse it on a tape on a aluminum stub. So you definitely want to, if you have small enough particles, you can just disperse this on a substrate like silicon, or you can put it on carbon tape. You just want to make sure that you remove all the loose particles before you put it in the SEM. The other option too is if your particles are small enough, you can put them on TEM birds, which you can easily mount in the SEM as well, and gives you the additive advantage where you can move between the SEM and the TEM with the same sample. So when doing when talking about sample prep, we talk about what you need to do to make your sample optimal for the technique you're going to use. So when you're doing EDS and EDSD, there are many considerations to take into account. So one of the biggest considerations is the interaction volume of your beam. So typically, if you're going to use EDS for EDSD, you want to use a higher voltage in the SEM, typically 20 kV or above. And you can use a program such as Casino or a DTSA to determine the trajectory of how deep these electrons interact into your sample. So when you're doing something like this, you want to consider your feature size because your interaction volume could be larger than the feature size. So if you're trying to do EDS, you might get mixed signals from deeper in the sample that also show up in your EDS. And this is especially important for EDSD and is a reason a lot of people have some issues getting good patterns. For example, if your interaction volume of your beam and your material is 2 microns, but there is 1 micron of damage on your damage layer, that's going to hinder your signal and you might not be able to distinguish the patterns. Okay, so I will shift right now into TEM sample preparation, and a lot of the techniques that I just mentioned are applicable for TEM. The SEM techniques are good for TEM as well. So generally the requirement for TEM or STEM observation is to sample under 100 nanometers thick. The thinner the better generally. So we generally use 2 methods of focused ion beam for mechanical preparation, but I'll also briefly discuss crushing your sample because that's the quickest way of doing it, and it might be overlooked in some cases. So in the FIB, you use ions, traditionally gallium, to lift out a small piece of a larger specimen. It's usually on the order of 10 microns, and then you use the beam to fit it to electron transparency. With mechanical preparation, you then use the sectioning that I mentioned earlier. You would cut put down a piece of your sample that's usually on the order of 1 to 2 millimeters by 1 to 2 millimeters, and you would progressively polish this down to under 100 microns and use something like argon milling to achieve electron transparency. And I'll go into a little bit more detail about that. So FIB is generally your best course if you need a site-specific area. So if you need a particular part or a particular device, there really isn't too many options other than FIB. So you can target that area. And FIB is also useful for in situ prep, TEM sample preparation, where you need to precisely mount your sample on a particular part of the grid. Disadvantages of FIB are you can impart significant damage to some of your samples based on the effects of the gallium implanting into your sample. In many cases, the lowest energy you can go to clean your sample in the FIB is 2 kV, which is much higher than what you could with a Argon. And I'll give an example later, but there are improvements being made nowadays to get ultra thin specimens, but that is still a challenge for some cases. So the PFIB is also available for TEM sample preparation. You can use the exact same way as the gallium FIB. There's just a couple differences in the interaction of xenon versus gallium in your material. So with gallium, you might have to deal with gallium implantation. If you have a polycrystalline material, you might find gallium segregates to your grain boundaries, which could be an issue in some cases. But xenon generally has a smaller interaction volume than gallium. So the advantage of the plasma fit is that you can do your initial steps much quicker. So as I mentioned, you can go up to microamps. You wouldn't want to use that for TEM sample prep, but you can typically cut your sample out very quickly. The trade-off is that when you do go to the final thinning, so the gallium fit has low currents, small spot size, and a high current density, which makes it good for precision thinning. When doing xenon, you have a high current, larger spot size, and a low current density. So in this case, it's difficult to precisely thin your sample. And to do it, it takes more care. So you have to be a little bit more careful for this. There are other techniques for optimizing fit samples. So there are systems that are available for argon ion milling your fit samples. And the advantage of this is that you can then do those low energy milling steps below 1 keV down to 100 of EV to progressively remove damage layers. Typically with argon systems, and you also have you could also have liquid nitrogen available if you need to use that to remove damage. So the nanomill is a system that we have here that's available for TEM sample preparation. In some cases, this other system that I'll talk about a little bit more in a few slides is meant for bulk specimens for polished specimens, but in some they have demonstrated that you can also use this to thin down your fit sample down to energies of 100 EV to remove those damage layers. So polishing for TEM samples, it's usually a little bit more challenging for a lot of people because it requires a little bit more dexterity, and you have to monitor your sample thickness as you polish it. But typically you would use a tripod like you would for the SEM. You would cut your sample down, generally on the order of a millimeter or two, polish one side down, progressively finer grits, and then something like colloidal silica, flip it, and then do the same thing again. And in this case, you want to get your sample down under 100 microns thick that you would then monitor under a optical microscope when you're trying to get this precisely thin. So you can see one example here. So you would mount your sample on one of these stubs with an adhesive like crystal bonds, and you would thin it down so that your samples overall thin at the edge. So using this tripod system, you can either just polish it flat as possible, or you can tilt your sample and form a wedge-shaped sample. And you can see here from an example of a sample that I prepared. So you can see that there's these fringes that appear, and that is usually something that appears when your sample is very thin at the edge. Just to note, you can't see these in metals because this arises from a band gap in your materials. And once you polish it down, you would attach it to one of these slot grits that you would then be able to put in its EV down. So with polishing, I mentioned wedge polishing, where you would change the angle on your tripod to have a wedge-shaped sample where the edge of your specimen is the thin part. One other technique that was historically and still is commonly used is dimpling, where you use a grinder to thin a circular region in your region of interest, and that will thin down that area and allow you to target that area for argon ion milling. But as I mentioned, you would typically start at a higher grit film, work down to a grit such as 0.1 micron diamond, do colloidal silica, and then once you have that sample thinned down, you attach your grit, and then it's ready for argon ion milling. So this is the type of system that's commonly used for that, where you would clamp your sample into a holder like this, and you would focus the beam on that region of interest. So a system like this one can perform thinning from 8 kV down to 100 kV. And just like mechanical polishing and tip polishing, you want to work your way down from higher energies to lower energies to remove any damage that you're causing from previous milling steps. And in this case, you can also use liquid nitrogen cooling, and you can adjust your gun geometry to, as you go to lower energies, generally you want to go to shallower angles so that you can clean your surface pretty well. And this, like all other steps in sample preparation, is iterative, where you would thin your sample, screen it, and then go back and forth. So in the past, this is the technique that I actually used for my PhD research. So the advantage here is that with the argon ion milling, you can find particular regions in your sample that are extremely thin, which are very useful for things like quantitative STEM. So for example, in a material like strontium titanate, where the unit cell is 3.9 angstrom, if your sample is 15 nanometers thick, you'll have about 40 atoms in that column. If you can get it down to 5 nanometers thick, you'll have 15. And that makes it a lot easier to simulate what's actually in the column, and compare your simulations to your images. So one interesting example here, this is a material that I studied, lead, manganese, and niobate. There are different cell lattice positions, but there are these short range chemically ordered regions where you have certain atom columns that are magnesium rich and some that are niobium rich. And due to due to C contrast and STEM, you can see if there's if certain atom columns are magnesium rich or niobium rich. As you can see here in this image, since these are these regions are short range ordered, if your sample was say 50 nanometers thick, you could have these short range ordered regions overlapping over the entire thickness, and you wouldn't see anything at a higher thickness. And I'll just briefly mention that a technique that is available is to just crush your samples. And this is probably the easiest way of making your sample. It's not applicable to everything, but you would basically use a mortar and pestle. This one is agate mortar and pestle. You would just basically crush your sample down. You could also add liquid nitrogen into the mortar and pestle to promote fracturing of your sample. So this is good for materials that are brittle, that don't go a lot of deformation under the crushing process. So if you were working on a metal that had a high ductility, this probably wouldn't be the best way of preparing your sample. But for ceramics, it can be very useful. But in this case, what you would want to do is crush your sample down finally. You could place your powder in a culturing tube with methanol, sonicate that, and then use a pipette to grab your solution from the top of the top of your tube, and then disperse that in a lacy carbon grid. So as I mentioned, if your materials are ductile or you care about observing deformation effects, you're definitely going to alter your sample by doing this. But the advantage is you can make your sample within an hour if it's applicable for you. But so just to conclude, there are dozens, maybe hundreds of options for preparing samples for SEM-TEM. This is for inorganic samples, probably also similar for biological samples. But that would be too much information for one presentation. There are some techniques that I haven't discussed that are also available. A microtome, where you would use basically a fine diamond knife to slice off a piece of your sample for microscopy, or electropolishing, which is commonly used in metallic samples. But overall, I would say there's no exact recipe that's good for every single material, and this process is usually a lot of trial and error, where you will try something, find out you can't do what you want to do in the microscope, and then you'll have to go back and try again. And then eventually they'll find a way. But for one material, next you can make small modifications and get your sample ready to go. And then thank you for your attention. If anybody has a question, and just a reminder of the next seminar, the next 3 over the next few months. The next one, September 30th.
Thanks, Matt, for giving a good talk on a lot of different things in microscopy. So I always agree that sample prep is probably one of the more important things. If you have a terrible sample, you're not getting a good data. So you can waste a lot of time and energy on the microscope doing that. So if anyone in person or online has questions, feel free to these put them in the Q&A section, or you can post them in the chat. We can answer them from there. So we have a few minutes, so if you have questions, go ahead.
One question. So it's about using the colloidal silica on the DM sample prep. Do you have any suggestions about how to clean that?
Oh,
So because from my previous experience, we get the colloidal silica stuck on the DM foil, and it's really hard to get it out. I don't know if you have any suggestions how we can clean that from the sample.
Yeah, definitely. So I definitely have run into that issue before, but I think a good way of starting is to so when you're polishing on the felt pad for the colloidal silica, there's the microorganic soap. So while your sample's still on there, use that to start cleaning up your sample. Once you have that made, then in any case, I would plasma clean my sample for probably 10 minutes. But the ion milling process removes a lot of that. So in many cases, I needed to do only minimal argon ion milling. And when I did that, you could put your sample in at 1 kV for 10 minutes, and that usually gets rid of most of it. So the combination of the ion milling and the plasma cleaning afterward is the best way of doing that. But just by using the microorganic soap or acetone and ethanol, that does not completely get rid of it. And I see that a lot in the STM as well.
Okay. So you usually always go with an ion milling after that, like ion
Yes.
milling. Yeah.
So even if it's not necessary, you can make a silicon sample, just plain silicon, without argon ion milling it with, and then just polishing it using colloidal silica because it's optimized for that. But in any case, I still would ion mill that sample for 15 minutes just because that gets rid of the particles. Unfortunately, they're very hard to remove any other way.
Thank you.
No problem.
So I think similar to that, but probably steps before that. If you have a sample that has multiple different hardnesses, that's softer material, harder material, how have you normally dealt with those? That gets to be problematic.
Yeah, so that's a bit challenging. So in certain instances, my experience with that is usually with samples that I've made in the FIP. And usually the best way of dealing with that is to have a very hard capping layer that helps to mitigate those effects. But yeah, generally I've had good experiences just argon milling it. That seems to do a sufficient job of it. But yeah, it's still an issue because things don't thin at a uniform rate. So I would generally say to continue to work to lower energies and changing your gun angles. That might help a little bit.
Yeah, I've had some samples I felt that company was working on thin ion mill, we're dealing with all that kind of stuff. So went the ion mill route, but
Yeah,
I wonder if there are other ways to deal with that.
there's a lot of ways of just modifying the recipe in the ion mill. I guess also if you can mill with different gases, that might give you different results.
For soft materials, so this is materials for inorganic materials, but for soft materials, what kind of stuff would you do there for kind of sample prep?
For soft materials?
Yeah, it could be inorganic, could be probably organic a little bit, but testing like microtoming and stuff like that. You want to talk about that? And that's mostly a little bit out of the wheelhouse this one, but
Yeah,
useful things that I suppose it comes well.
I mean, in the past, I have made a TEM sample of a polymer by just sandwiching it between silicon and just thinning it down that way, and just using that as like a support to hold it down, and then you can just use the argon mill to thin that specific area. So that's one experience. You could, I mean, if you had, say, like larger nanoparticles, hundreds of nanometers, you could also disperse those. You could cut 2 pieces of silicon. You could use the adhesive M bonds and just disperse your particles in there, and then just thin that down, and then you can argonize and leave your particles, and that seems to work. So, but unfortunately, my experience in that is a little bit limited, but yeah.
Yeah, so that's fun having different ideas on how to do things.
Yeah, if you have enough of the sample, you can try anything.
I haven't seen any questions come in from online, so if anyone online has questions, so hang out for a little bit on those, or you guys in person have more questions about sample prep a little bit more.
Yeah, so if anybody listening does end up having a question, Dan and I have our emails here, so feel free to contact us if you have anything that you'd like to ask.